So in this video we're continuing to think about stopping distance, but we're now going to actually look at some data here, okay? So what we've got here is this. This is some data that's come basically out of the highway code, and what you've got here is different speeds. Now usually if you look in the highway code, these speeds will be in miles per hour, okay, because that's what we use in cars in the UK. It's an imperial unit, not a metric unit. It's a bit odd because in the UK we use a mix of imperial and metric, but in physics we talk about meters per second. That's the standard unit of speed or velocity, so I've changed all these into meters per second, okay? So 9 meters per second, 13.5 meters per second, 18 meters per second, and so on. Okay, so 9 meters per second is about 20 miles an hour. 13.5 meters per second is about 30 miles an hour. 40, 50, 60, 70 miles an hour. Okay, so you get the idea. Now, what we've got here then is this is your stopping distance. So your total stopping distance here, if we look at 9 meters per second here, your total stopping distance is 12 meters. Okay, that's the stopping distance. Okay, now that's made up of two components. This is your thinking distance, okay, and this is your braking distance. So as we know, stopping distance is equal to thinking plus braking distance, okay? So 6 plus 6 makes 12. So these are your thinking distances, these are your braking distances, and the stopping distances is the sum of the two, okay? So 96 meters here for a car travelling at 70 miles an hour to stop, okay? 21 meters of that is you actually reacting and thinking. So if you're travelling at 70 miles an hour or 32 meters per second and you need to stop, you're going to travel 21 meters, okay? If you see some object that causes you to need to make an emergency stop, you're going to travel about 21 meters just during the time that it takes to react to the situation before you actually hit the brakes, and then a further 75 meters is the distance travelled whilst your car is braking, okay? The distance travelled under braking, under the effect of the brakes. Right, so let's think about this a little bit more detail here now. So the first thing is this. You'll notice that for thinking distance, there's an interesting pattern here, okay? We don't know what this number is here. We'll work it out in a minute, but you can probably figure it out yourself. When we go from 9 meters per second to 13.5 meters per second, or 20 miles an hour to 30 miles an hour, you can see that the distance here, the thinking distance, has gone up from 6 to 9. Then up to 12, then up to, well, you can guess, then up to 18, then up to 21, okay? So if you double your speed from 9 to 18 meters per second, your thinking distance doubles, okay? And if you were to double your speed again from 18 up to 36, it would double again, okay? But we don't actually have that data on here, all right? So basically, when you double your speed, your thinking distance doubles, all right? Now, if you double the speed here from 13.5 to 27 meters per second, you can see again your thinking distance doubles from 9 to 18. Okay, so that is the relationship. Every time you double your speed, your thinking distance doubles. Okay, now why is that the case? Well, if you think about the equation, the basic equation linking speed to distance and time is speed equals distance divided by time. So if we rearrange that equation, time is equal to distance is equal to speed times time. That's what we're looking for, okay? So your thinking distance can be calculated, what am I doing here? Can be calculated from your thinking distance is equal to the speed multiplied by the time. Now what is that time? It's your reaction time. Now sometimes we call this the thinking time. So your thinking distance is equal to your speed multiplied by your thinking time. Now, it doesn't matter whether you call it thinking time or reaction time, it's the same thing, but just watch out in the exam. If they call it the thinking time, it means reaction time. It's the same thing, okay? Now, if you think about this, your reaction time, let's just say your reaction time is 0.5 seconds, okay? 0.5 seconds, your reaction time or your thinking time, same thing, okay? So that is constant, okay? Your reaction time is not affected by the speed that you're going at. Whatever speed you're travelling at, your reaction time is always the same. The only thing that's going to affect your reaction time is if you are not thinking straight or you're distracted or whatever, and we'll talk about that in a bit more detail later. But your reaction time is always the same, provided you're in a sort of state of normal awareness, so to speak. Doesn't matter what speed you're going at, your reaction time or your thinking time stays the same. It's really important to get your head around that because people don't understand that. Reaction time is always the same no matter what speed you're going at. Now, so we know what your reaction time is, okay? We know that your thinking distance is going to be equal to some sort of speed, whatever it is, okay? Some sort of speed. Let's say it's 9 meters per second. It's going to be 9 meters per second multiplied by 0.5 seconds. What does that give you? Well, if you were to work that out, you'd have 9 multiplied by 0.5. Obviously, it's going to give you 4.5 meters, okay? Now, that doesn't match up with this, and that's because I've used an ambitious reaction time here, okay? This is somebody who's got really good reactions, whereas the data here is for the average person, and you have to take into account then young people, old people, people with a variety of reaction times. So this is clearly not the reaction time or thinking time used in this data, but this is just used for illustration purposes here. Let's think then of your thinking distance. Let's say that your thinking distance now is equal to 18 meters per second. So now your speed has gone up from 9 meters per second to 18 meters per second. We doubled our speed. Your reaction time is going to stay the same. So your thinking distance now will be 9 meters, okay? So the fact that your reaction time stays the same means that thinking distance is directly proportional to your speed. So basically, if you double the speed, your thinking distance will double. If you increase your speed by a factor of a half, your thinking distance will increase by a factor of a half, and so on, okay? They are proportional, all right? So that's the thinking distance. Now, the braking distance is a bit different, okay? So remember, these were just illustrative calculations. They don't match up with the data here, and we'll come back to that data afterwards. Now, the braking distance doesn't quite work the same. You can see here that when you double your speed from 9 to 18 meters per second, that your braking distance is not doubling, okay? Actually, you can see there is a relationship though. 6, 12, 18, 24. When you double your speed, your braking distance quadruples, okay? You can see here 13.5 meters per second and 27 meters per second, double the speed, okay? And the braking distance here basically quadruples, okay? So 14, 28, 42, and it should be 56. Now the reason here it's 55 is just because of some rounding issues, okay, in the data. But when you double your speed, the braking distance quadruples, okay? So it should be 56 there. Now, that's the relationship, okay? When you double the speed, the braking distance quadruples. Why is that the case? Well, it's because of this. The kinetic energy, you'll do this later in the course, the kinetic energy of an object is given by half mv squared. Where that's the kinetic energy, that's the mass of the car, and this is the velocity squared. Okay, or we can say speed squared here, it doesn't really matter. Okay, so what you can see in this relationship here, we don't need to worry about the mass because the mass of the car is going to stay the same, but we know that the kinetic energy is equal to half mv squared. So when you double your speed, because it's squared, the kinetic energy quadruples, okay? So that's the reason that the braking distance quadruples. When your speed doubles, your kinetic energy quadruples. So that means you've got 4 times the amount of energy to get rid of under braking to convert it into heat, remember? We convert kinetic energy into heat. So when you double your speed, you've got 4 times the amount of kinetic energy to convert it to heat, and that means that your braking distance is 4 times as long. Okay? There we go.